Okay, so welcome back, everyone. We are ready to begin Unit 2 and to really dive into the meat of this course, which is how do transistors work. A very powerful way to understand transistors is through the use of energy band diagrams. Now, that's what we'll be discussing in the next lecture. For those of you who need a quick review of what energy band diagrams are, how we draw them, and how we interpret them, that's what I'd like to do in this lecture. So an energy band diagram, just to remind you, is a plot of the bottom of the conduction band and the top of the valence band versus position. Energy band diagrams are a very powerful technique for developing a qualitative understanding to the solution of a set of semiconductor equations. Usually the first step in understanding a device is to draw an energy band diagram, and if we can understand the operation in terms of energy band diagrams, then we're prepared to write down a few equations and solve the equations and get analytical expressions. So another thing I would like to remind you of is the fact that in equilibrium, the Fermi level is constant. It's independent of position. So one way to see that is if you remember that we often write the current as proportional to the gradient of the quasi-Fermi level. This quantity F sub n here is the quasi-Fermi level. In equilibrium, the quasi-Fermi level is the Fermi level. So in equilibrium, we would say the current is the gradient of the Fermi level, but almost by definition, the current is zero in equilibrium. In equilibrium, nothing is happening. We can't extract energy out of a semiconductor device that is just sitting there in equilibrium. So in equilibrium, the current is zero, and the current equation then implies that the Fermi level must be independent of position. So that's a very important fact to remember. Now, energy band diagrams are all about band bending. So we're going to try to understand what makes bands bend. So here's an energy band diagram for a p-type semiconductor. Here's my conduction band. Here's my valence band. The intrinsic level is approximately the middle of the band gap, and my Fermi level is down near the valence band, so this is a p-type semiconductor. So that's an energy band diagram. Now, when we make a MOS transistor, we will make a metal oxide semiconductor structure. So let's do that here. And let's ask ourselves, what would happen if we applied a positive voltage to this gate electrode? Well, first of all, the semiconductor will stay in equilibrium because we have this insulating gate oxide here. Current can't flow through that insulator. So there's no current flowing. The semiconductor stays in equilibrium. The metal stays in equilibrium. The Fermi level is flat even when we apply a voltage. But what we would like to ask ourselves is what happens to this energy band diagram when we apply a voltage? Okay. So I'll remind you of something that you probably have seen in a previous semiconductor course or in a freshman physics course, and that is that if you have an electron and you have a positive voltage, that positive voltage would attract the electron to the plate, pull it down into a potential well. It would lower the energy of the electron. So the important point to remember is that a positive potential lowers the energy of an electron because it has a negative charge. A negative potential would increase the energy of the electron, the potential energy. So energy is minus Q times voltage. That'll allow us to figure out how the bands will bend. So if I have my structure, and if I have a positive voltage on the gate, and if I have the right side of the semiconductor grounded so the voltage is zero, then the voltage is going to go in the semiconductor. The voltage near the positive voltage on the gate is going to be positive. And it will eventually end up at zero deep inside the semiconductor. So the electrostatic potential versus position is going to do something like this. Zero in the bulk. As we get closer to the surface and we can sense the fact that there's a positive voltage on the gate, the potential increases. Now, what happens when the potential increases? The electron potential energy goes down. So the potential energy of the electron is the bottom of the conduction band, but that is where it was, say, deep in the semiconductor where the potential was zero. But then if at some position I have a positive potential, the electron energy will be lower because of that positive potential. So the conduction band will bend down if the potential is going up near the surface. The valence band will bend down because it's just one band gap below the conduction band. The intrinsic level will bend down. The Fermi level won't bend because I'm in equilibrium. The Fermi level is constant. So that's what my energy band diagram would look like in this particular case. That's a simple energy band diagram, but it actually tells us quite a lot about what's going on in there. One thing that we can see immediately is that if I take the slope of the conduction band, or of the valence band, or of the intrinsic level, that slope is related to the gradient of the electrostatic potential, actually minus the gradient of the electrostatic potential, which is the electric field. So that slope is Q times the electric field. So looking at this energy band diagram, we can see where the electric field is large, whether it's positive or negative or zero, just by looking at the slope. Now, we also know that the electron density is related to the distance between the Fermi level and the intrinsic level. If the Fermi level is above the intrinsic level, we have a lot of electrons. If the Fermi level is below the intrinsic level, we have a lot of holes and fewer electrons. So as we look at this, the hole concentration is related in the opposite way. The further below the intrinsic level the Fermi level is, the more holes that we have. So we can look on a band diagram like this and we can see that there are a lot of holes in the bulk and there are many more electrons near the surface because the Fermi level is above the intrinsic level near the surface. So we can sketch out the electron profiles as well. So the first step in thinking about a device would be to draw its energy band diagram. If we're drawing an energy band diagram in equilibrium, we'll have a Fermi level that's independent of position, and then we need to deduce how the bands bend. The second part of using energy band diagrams is to read the energy band diagrams and extract some useful information from it. So we know that electrostatic potential, when the electrostatic potential goes up, the electron energy goes down. So the potential versus position is just minus the electron energy versus position with a Q in there. The electric field is proportional to the slope of the conduction band versus position, or valence band, or intrinsic level. The carrier densities, N, is proportional to the log of N is proportional to the separation between the Fermi level and the intrinsic level. So I can see that I have a lot of electrons here, and I don't have very many electrons here at all. The hole concentration is the same, is proportional to how far below the intrinsic level the Fermi level is. So I have a lot of holes over here. And if I want the charge density, I can remember the Poisson equation says that divergence D is equal to space charge density. So the slope of the electric field is proportional to the space charge density. That means I have to take the second derivative of the energy band diagram. That can sometimes be a little bit difficult since we're drawing these energy band diagrams qualitatively. Taking its first derivative is okay. Taking its second derivative sometimes can be a little difficult. So sometimes there are other ways that we can sneak up on it and deduce what the charge density is. So just for practice, take this energy band diagram and make a sketch of the electrostatic potential versus position, the electric field versus position, the electron density versus position, the hole density versus position, and the space charge density versus position. See if you can do that as a review. So here's another example of a little more complicated device. This is an NP junction. Here's an N-type semiconductor. Here's a P-type semiconductor. Each one is uniformly doped. We put them together and we expect something to happen at the interface between these two regions. Very far to the left, we would just expect to see an energy band diagram of an N-type semiconductor. Very far to the right, we would just expect to see an energy band diagram of a P-type semiconductor. Near the middle, we would expect to see something different happen. There'd be a transition region. So what we need to do is to draw an energy band diagram of this NP junction. The way we would do that is we would begin, if we're looking for an equilibrium energy band diagram, we'll simply draw a straight line. That'll be our Fermi level that is constant and independent of position. And then we'll draw the energy band diagrams where we know them. At the two ends, we know at one end we have an N-type, at the other end we have a P-type. We're far away from the transition region. We can just draw an energy band diagram for the semiconductors at those two endpoints. and then we smoothly connect those two regions. Once we have the energy band diagram, we read it and pull off the information that we're after, and you can extract quite a lot of information from an energy band diagram. So this is what you would find from that procedure. Way out here to the left, we just see a uniform N-type semiconductor. N-type because the Fermi level is near the conduction band, way above the intrinsic level. Over here to the right, we just see a uniform P-type semiconductor. The Fermi level is well below the intrinsic level, tells us it's a P-type. Closer to the top of the valence band, again, tells us it's a P-type semiconductor. And then we smoothly connect everything up in the transition region so that there are no discontinuities there. That's our energy band diagram for the NP junction in equilibrium. All right. So bands are flat way out to the left, bands are flat way out to the right, and there's a transition region in the middle. Okay, now we want to read this energy band diagram. We'd like to extract the electrostatic potential versus position, the electric field versus position, the electron and hole densities versus position, and the space charge density versus position. So let's see if we can do that. The electrostatic potential. Okay, well, we know that whenever the potential goes up, the electron energy goes down, so we simply need to take the conduction band versus position and flip it upside down. That's all that would require. Flip it upside down, we would get an electrostatic potential versus position that would look like this. You know, the precise value over here depends on what reference we chose. Very often we might choose this point to be 0 and call that our reference. And then the potential would increase as we go to the left. Okay. So you can see that there is some potential difference between the N side and the P side once we put the two together. This difference is called the built-in voltage of the PN junction. So how about electric field? So we remember that the electric field is proportional to the slope of the energy band, conduction band or valence band, whatever. So all we have to do is to take the slope. It's 0 here, it's positive in the transition region, it's 0 in the P-type region. So if we plotted the electric field versus position, we would see that it peaks in the transition region. Okay. If we're interested in carrier densities, we know that the carrier density, the electron density, is determined by how far above the intrinsic level the Fermi level is. So we have a lot of electrons here. We have fewer and fewer and fewer. And then when the Fermi level goes below the intrinsic level, the electrons become minority carriers and we have even fewer of them. Just the opposite thing happens for holes. The hole concentration is determined by how far below the Fermi level, how far below the intrinsic level the Fermi level is. So we have a lot of holes over here on the P side, fewer and fewer holes. We go over to the N side, the Fermi level is far above the valence band, far above the intrinsic level. We have a few minority carrier holes. So we can just sketch these out. The electron concentration goes from a high value on the N side to a low value on the P side. The hole concentration goes from a high value on the P side to a low value on the N side. We can just sketch that out from the energy band diagram. Notice in the transition region, notice this is a log plot. So in the transition region, we don't have very many electrons or holes. So that's going to be important because it'll help us figure out the space charge density in a minute. So let's look at the space charge density. One way to get the space charge density is to take the second derivative of the conduction band. So if we were able to do that carefully, we could get a nice representation of the space charge density. That might be a little bit difficult to do when you're trying to eyeball things on a plot like this. So there's another way that we could try to get a handle at the space charge density. And that is by looking at the space charge density is the concentration of holes, positive charged, minus the concentration of negatively charged electrons, plus the concentration of positively charged ionized donors, minus the concentration of negatively charged ionized acceptors. Well, we've already deduced how these carrier densities vary. We know that on the left side we have a uniform concentration of N-type dopants. On the right side we have a uniform concentration of P-type dopants. And we showed that in the middle region here we don't have very many electrons or holes. We only have ionized dopants. So that allows us to sketch out the space charge density. On the left side of the transition, we mostly just have ionized donors, positively charged. Not many electrons or holes to worry about. On the P side of the junction, we mostly have ionized acceptors, which are negatively charged, and not many electrons or holes to worry about. We call that a depletion region. Once we get deep into the semiconductor on each side, we have a neutral semiconductor where we have an equal number of negatively charged electrons and positively charged donors, and the net charge is 0. So we can deduce the space charge density that way if we don't want to try to take a second derivative of the energy band diagram. So just to summarize, these energy band diagrams are very useful for providing a qualitative solution to the semiconductor equations. If we want numerical answers, we would solve these continuity equations for electrons and holes self-consistently with the Poisson equation to account for their charge. That would be the way to get quantitative numerical answers. But energy band diagrams are a remarkably simple way to get qualitative insight into what the solutions to these equations are like. So that's what they're useful for. Now, with that review of energy band diagrams, or introduction for those of you who haven't seen that before, in the next lecture, we will draw energy band diagrams of MOSFETs, and we will find out that this is a very simple, very physical way to understand how MOSFETs operate.